Thanks for inviting me to this nice workshop. I'll give you some brief overview about our benchmarking efforts over the past couple years, and then some recent new addition and hopefully future directions. We'll talk about this, and hopefully we find some common ground and can work on this together. So what's the problem? Oops. And it's not moving. Good, then I take the arrow keys. So basically I will not go into too much detail. I will just give you some high level, but basically it's the presentation is designed to get some collaboration started and to build better supercomputers in the future. Since, as Alex said, we can only optimize what we understand and what we can measure. So in terms of motivation, basically, we are seeing a Cambrian explosion in architecture choices, especially with the deep learning coming up and everyone trying to build deep learning chips nowadays. So you have like 50 plus different potential architectures for the future on top of the traditional stuff. And there are so many choices of things you can use for your data center, for your HPC system, for your supercomputer, that it becomes really a hassle to make sense of it. Because we have like potential phone chips, FPGAs, we have different programming languages, which are like traditional ones like Fortran, or more novel ones like Julia. We have more novel containerization stuff going on, and workloads like deep learning, and then on top of the traditional simulation workloads. So how do we make sense of it? How do we determine the best architecture for a particular site? I mean, like, you can't say that's the best architecture. You can only say that's the best architecture for my site, usually, because people run different stuff in different regions of the world. So, and the other challenge we see is a scale out. Because of the end of Moore's law, we will see bigger and bigger systems. We already have that in Fugaku with like almost 160,000 compute nodes, a diverse set of network architectures. So the systems are increasing, they're becoming more and more complex. They are integrating more and more diverse architectures, like different networking topologies and different networking hardware like InfiniBand and Tofu and Ethernet all together crammed into the same system. So how do we approach that? Traditionally, we have done that with proxy apps. So for example, I've used proxy apps a while back in Tokyo Tech when we did a study about comparison between a fat tree and a HyperX. So we built out of a decommissioned system in Tokyo Tech, the Tsubamis 2 system. We took it apart because it had a dual rail fat tree network, and we took one of the networks and built it into a HyperX as a testbed, and then compared this like multi-petaflop system on two different networking topologies to see which applications perform well on which architecture, because theoretically the HyperX has some advantages in terms of cost saving and in terms of bisection bandwidth and latency as well. So we did this study. We also had to fix a few other things because our older hardware, the InfiniBand hardware, was not capable of certain adaptive routing you would need for this type of HyperX topology, which is designed with like adaptive routing in mind, and QDR InfiniBand didn't have that. So we had to implement some mitigation strategies. So what we essentially did was we threw multiple MPI benchmarks, 9 HPC proxy applications, and also top 500 benchmarks onto this system with the two networking topologies, and we measured them individually. So we threw the apps onto the system, measured one, and then turned off this rail, this networking segment, and then turned off on the other one, and then ran the same benchmarks, side-by-side comparison. And we actually found out that this HyperX topology performs quite well despite the lack of adaptive routing. And for certain applications, it even outperformed the traditional factory topology, which was quite remarkable. And so that gives some hope that we can build cheaper systems in the future. So another thing we did with proxy applications was a study of double precision floating point units. Basically, people always say that HPC is like double precision heavy, and we wanted to investigate this with our proxy applications. So we even extended the amount of proxy applications we had in our test suite for this test. And why do we do this? Basically, if we know that our applications don't need as much double precision units, then theoretically we could use less of them in our CPUs, which saves power, which saves chip array, which we then could use for other types of floating point units, for example, tensor floats, like tensor cores or something else, which I will come to in a few minutes. Because we studied this as well. But basically you can do a lot of things if you can reduce the amount of double precision units because they're quite heavy in terms of silicon area. And we did this comparison with our proxy apps on two different Intel CPUs, the Knights Landing and Knights Mill. And so we analyzed a bunch of different proxy applications in terms of if they use integer, the blue bars, if they use double precision floating point units, which was the red bars, and single precision floating point, which is the green bars, and we see they are quite integer and double precision heavy. So we went even further and we tried to analyze, even so they are using a lot of double precision, are they actually relying their performance on double precision or not? So we compared those two architectures which have different amount of double precision units. So the KNL has twice as many double precision units than the KNM. And theoretically, we would expect that applications which are floating point heavy would benefit from that, from the KNL architecture a lot and would suffer on the KNM. But oddly enough, we found out that most of the apps, except for a few, actually don't suffer from the lack of the double precision floating point units. And a few even don't use double precision at all, like Minitry, for example, which is only triangle counting on graphs. And what we also found out in the study is that most of the applications are actually memory bound and not compute bound. So as you see here on the roofline, and the way to optimize that is actually to invest more into memory-centric architectures instead of double precision floating point units. So we could throw them away and use something else, do something else with the silicon area, what we are already investigating right now at the moment with our SC paper, for example. So people should brace for basically less floating point units because of market forces and also because of HPC applications are more memory bound and don't need that much floating point units, and therefore we should restructure our architectures potentially in the future. And then, yeah. So another thing we investigated with the proxy applications is basically how much double precision, how much dgem we need. What also many think when they start HPC is that HPC applications are primarily matrix multiplications, dense matrix multiplications. That's what you get taught in school. You start with like, here's a matrix, multiply them and see what the performance looks like. And so we wanted to investigate how do our applications actually look? And is that a true statement from like what people learn when they begin with HPC? Similar again, we could potentially, if we know that applications are matrix heavy, then we can invest in tensor cores or similar type of units on a CPU, for example, or optimize other things of the hardware. So we did this study and published this last year in IBDBS, and we investigated, for example, historical data from the K-computer, where we only saw that 50% of the node hours were actually consumed by applications which have gem functions inside. It doesn't mean that they were calling a gem, because we only had like access to the symbol tables. We didn't have access to exactly logs to like function calls to libraries. So, but we know that only 50% were actually running. 50% of the node hours are actually consumed by those apps. Similar, we did a investigation of the Spark packages. Probably most of you know those. And we found that similar there, only 50% have some direct or indirect dependency on BLAS functions. And then we did a study of the tensor cores, how beneficial they are for deep learning. And we found out that some kernels in machine learning actually benefit from tensor cores, while others only get a marginal benefit. So for example, theoretically, the tensor cores should give you in those examples up to like 8x speedup. But in most cases, except for like GEM, we don't get that much speedup from the tensor cores. So even for those type of machine learning kernels, which are present in MLPerf, for example, we don't get much speed up from the tensor cores. Even so, that may change, as Alex will probably tell you in the future, since the landscape of machine learning is also rapidly changing. And then we investigated our traditional HPC applications. So we used 77 HPC benchmarks from the ECP, from RIKEN, which were designed for the exascale systems right now as basically proxy applications, co-design apps. We investigated the top 500 list, different spec packages. And so we checked how much GGEM do we have in those, how much BLAS operations which are not DGEM or GEM in general, and then LAPAC, and then everything else. And what you see is kind of depressing picture, or like depending on if you like tensor cores or not, it might be an optimistic picture that most of the apps actually don't need any GEM operations. But what is also surprising, most apps actually also don't utilize BLAS or ScalaPack, which is a little bit frightening that everyone hand codes their own functions, which they also could also outsource to libraries. So that was the study of the matrix engines, and basically based on this data, we then investigated and did some thought experiment. Basically, we investigated how many cycles per HPC center are spent in certain domain areas like climate science, like QCD, CFD simulations, etc. Then we used the applications we investigated, selected the application with the highest amount of GEM, and let this application represent the chunk of like domain, basically. And then extrapolated how much benefit a potential matrix engine, like a tensor core or something like that, would give the system if you would introduce that into the system and you get some speed up from that. And then we assumed like a 2x speed up, 4x speed up, 8x up to infinity, basically. And we checked that for the K-computer data we had available, the Oregon National Lab system, and the theoretical future system, where we basically said, okay, every app gets like 10%, and then deep learning is represented by 20% because we expect the future system to be quite deep learning heavy. And we see that for the K-computer there was almost no benefit, was like a few percent. Argonne National Lab benefits a little bit better, like 10% if you assume 4x speed up, but if you assume infinity, it doesn't get much better. And then for like a hypothetical system with a lot of deep learning running on it, you would get like a almost 25%, in this case 23.8% speed up, which is noticeable, but I don't know if that is enough to justify certain types of CPUs you would need for that, and spending the silicon area on that. And maybe it's better to spend the silicon area on other things, like memory, acceleration of the memory bottlenecks, for example. Yeah. So basically, what we have also done, I won't go into too much detail about this, but was a comparison based on the proxy apps of different compilers for the HPC, for the supercomputer Fugaku. And we found out that depending on the compiler selection, you can get tremendous benefit in certain cases. And we had like over 100 workloads selected for that. So we are building up our benchmarking suite over time, basically. So we started with 9 plus a little bit, and now we are at like 100 plus. And as I said, I won't go too much into detail about this. Basically, the finding was that the recommended usage model may not be always the best, which was 4 ranks and 12 threads. So in some cases, certain proxy applications benefit from other types of assignments where you have like 1 rank per node and 48 threads for the A64X chips. And then we also didn't find the silver bullet compiler yet for the A64X. But we know that based on certain trends in those proxy applications, we can give recommendations. For example, we can say that Fujitsu compilers are better for Fortran, and Clang-based compilers are better for C++ codes, especially C++ codes, where Fujitsu compiler doesn't shine that much. And we, based on this, we actually recommended for the operations team and helped them to install a new LLVM backend, which can be used as an alternative to the Fujitsu compiler suite. But yeah, overall, many years later, we are basically drowning in proxy applications. We have hundreds of them, like the HPC Challenge Benchmark ECP, Coral Benchmarks Fiber, Spec, etc. And many of them are actually overlapping, as you can see from the cosine similarity metric, which have other people have analyzed. And we still have like many more benchmarks besides those benchmark suites. And what we have learned from this is that they're inherently complex and there are implementation biases because they're written in certain languages, tuned over years, assume certain CPU backends underneath. So there's basically a long year of like implementation bias in them. The maintenance overhead is quite large. And there's in some cases not sufficient testing and documentation done. So we had some issues with certain non-standard or like crashes with other compilers or like things with numeric instability when you change compiler flags or compilers in general. So what do we do with that? Basically, we got together with DOE and we say octopods to the rescue, and I will now go a little bit into detail into the future, what we are thinking of how we should change the approach with proxy apps. Basically, we want to have an alternative to proxy apps, which are our so-called octopods. And basically what we think is that they are sitting in between the dwarfs, HPC dwarfs or Berkeley dwarfs, and the proxy applications. So proxy applications are too high level, too like tuned and too application specific, and the dwarfs are too low level and like they can't really match the application behavior, and we want to have something in between. So we envision a set of highly parameterizable and changeable dwarf-like problem representation, which act as kind of a co-design target where like system operators will understand what we are talking about, where domain scientists will understand what we are talking about, and where everyone can come together and work on a smaller set than like hundreds of proxy applications. And we can theoretically use those to apply machine learning to identify those type of kernels inside of real applications, parameterize those octopods to match the specific parts of a real application, and then categorize compute phases, for example. So we have a paper which will come out soon, written up already. And I will just give you an example of one of those octopods we envision, and it's basically the trivial matrix multiplication. I said matrix multiplication is not that important, but hear me out. It's just like one octopod because some people still use it in certain codes. So what we envision is that you have like a parameterizable octopod, which is like you can have different input shapes, you can have different precisions, you can have batched, non-batched, dense, sparse, etc. So you all do this in one single octopod, which is your matrix multiplication, instead of just doing HPL. And then we use that, and we can, depending on the input configuration, we can match that to a certain application or section in the application. And we want to use that as for co-design, as I already mentioned. We can use that for performance modeling. We can use that for the vendors because then if they can accurately estimate based on proxies what applications will look like, then they don't oversell hardware, for example. We can use that for porting efforts. We can use like a octopod to give that to a user and tell him, here, this is how you have, the octopod was changed for this particular hardware, and with this octopod, this matches your part of your application, so you can use the same tuning mechanisms which we used for the octopod to apply and match your application to the future hardware, for example. And in general, there also, since we can change them depending on size, depending on configuration, they are potentially better suited for co-design tools. For example, high fidelity simulators like Gem5 or Codes and so on. So with that, I summarize, we need a lot of better tools. There are a lot of R&D challenges ahead. We need better test beds to understand what's going on, and better basically proxies, which we call octopods. And I hope with that I can enlist you to help with our proxy apps in the future, or like octopods in the future, or if you're interested in collaborating or in general job opportunities, RIKEN is hiring, or if you want to have access to Fugaku or you have interested students, then we welcome you more than enough. And with that, I'm through with my slides, and I will give it back to Alex, and I'm open for questions.